So I'll give a short introduction to this session. So, and then after me, you will have presentations from the mission scientists and mission managers who are in charge of each of the different satellite missions. So you heard from our Director General earlier this morning. We are building a number of different types of satellites. So both meteorological, the operational Copernicus satellites that we do for Commission, and also our ESA Earth Explorer, so more scientific satellites. So building satellites is a key thing for ESA, and then which is important is when we have built the satellites, also to manage these missions and to distribute the data. Other activities that do in Earth observation, you have seen it a bit from my presentation and from Anna Maria. It's more this applying the data part. And then we have some other activities, innovation and commercialization. So now you will hear more from those who work on managing the mission and also for developing them in the sense of being responsible a bit for preparing preparing the satellites. So yeah, these were these three different strands, as I mentioned: meteorology, Copernicus, and science. I don't go into details with them now, but for the Copernicus one, which are the most in focus in this training, we have these six existing satellites. So already with this, it's really a fantastic Earth observation program, a fantastic system of satellites with these 6 families. And you will hear more of them now from 3 of these satellites, Sentinel-1, 2, and 3, which are the most relevant for snow and glaciers. And then, if that was not enough, we are now preparing 6 other families on top, so it will be doubly fantastic program, the Copernicus program. And you will also hear from here. You will hear about 3 of these, 4, in fact, of these new satellite missions, which are the most relevant for snow and glaciers. So, with that, do you hear me now, Nuno? You are muted, Nuno. So with that, yes, perfect. Yeah. So now I will give the word to Nuno Miranda, who is the mission manager for Sentinel-1. So please, Nuno, if you can share your presentation.
Let me share the screen. How am I going to do that? Do you see my screen? Do you see my presentation?
Yes, yes. It's not in presentation mode yet, but we see it.
Yeah, I won't go to presentation mode because there are some issues in my presentation. So if you don't mind, I'll stay like this. Okay. Can you see okay?
Is it okay? Yep.
Okay, good. So thank you very much. I am Nuno Miranda. I am the Sentinel-1 mission manager, and I think I have 10 minutes to make you a brief overview of what is Sentinel-1. So it's pretty short, so I have to remove a lot of slides. So
yes. If you could try to limit it around 7 minutes, so we have a couple of minutes for question as well, okay. It would be great. Yeah.
I'll try. So let's start from here. This is Sentinel-1 platform that has been developed by our colleagues of Thales Alenia Space here in Italy. And it's a platform basically that is shared with other missions like Cosmos Max, Ganymede, or I think RADARSAT-2. It carries a unique payload so far, which is the SAR-band antenna, which is, you can see here, which is 12 meter long by almost 1 meter wide. Do you see my mouse moving? I think yes. Huh? And the other most visible element of this platform is, of course, the solar arrays, because the SAR being an active instrument, it requires a lot of power to be generated.
Sorry, Nuno, should we see something moving, you said? You moved to the slide, or? On the mouse. Okay. Yes, fine.
So SAR being active requires a lot of power, much more than other type of payloads. So that's why we have this beast also in terms of solar arrays. I think that if you had a presentation from our DG, you have seen that this is our ESA EU programs articulated around 3 main pillars: the science, where we develop specific instruments to answer specific scientific needs; the Copernicus programs, we'll see that, where we have the Sentinels that are basically here to allow the development of commercial applications, operational services, and allow the implementation of the European policy and the Meteo satellite that are developed by ESA and operated by EUMETSAT. I'll go quick on that because I think that you have seen that. Overall, you can see that in terms of SAR, we are preparing. We are now operating Sentinel-1B, 1A and B. We are working towards the replenishment of this first generation of Sentinel-1 with the launch soon of Sentinel-1C and D. And basically, we are preparing also already now the second generation of Sentinel-1 with Sentinel-1 next generation. And I think that you'll have a specific presentation from Roselle later. There are few other instruments in the science elements like biomass at P-band and Harmony that will also be soon launched in space that will be fantastic new opportunities for you working with this data. So it's very important to know what ESA is doing, but there is not only ESA. I think that the purpose of these slides aims at illustrating how lucky you are. When I started working in ESA in the late 90s, I was just working with ERS-1, 2, and RADARSAT-1, and you can see that in a couple of in the range of few decades, the landscape has totally changed, and it's really important to remember that the Sentinel-1 mission really stands on the shoulders of its precursors like ERS and VSAT, the Canadian RADARSAT missions, and those have allowed to develop most, if not all, the applications that you are working on so far, and has really contributed to developing the European leadership in terms of Earth observation. So, in a nutshell, this is what is the Sentinel-1 mission is. It's a constellation of two identical SAR C-band satellites, the A and B units that will be soon replaced by the C and D units. They are located in the same orbital plane, located at 180 degrees apart, at around 700 kilometers altitude. They are designed for an operational lifetime of 7 years. The quarter of the year that you can see here is for the commissioning phase, but operationally it's 7 years. And each satellite have a repeat cycle of 12 days. And if you consider the two satellites flying, it's a repeat cycle of 6 days. In terms of payload, we have a SAR, a synthetic aperture radar, working at C-band with dual pole capabilities. I think it's important to mention that I believe, to my knowledge, Sentinel-1 has been the first mission systematically using the dual pole as a main mode of operation, and this has been a game changer for many applications over land. We have a very stringent radiometric accuracy of 1 dB. This also is something really important for people like you that are using this data for retrieving geophysical variables. It's really important to have a very radiometric, very stringent radiometric accuracy. And we have a fairly good, let's say, noise equivalent sigma 0. For Sentinel-1C and D, there will be a new payload that will be associated to the SAR, that is the AIS, for supporting instrument marine surveillance. In terms of imaging modes, we have 4 exclusive imaging modes. Strip map, that is a legacy mode from ERS and NVSAT that we're almost not using anymore. Our main horse is for observation over the landmass is IWS, the interferometric wide swath mode, and that has a swath of 250 kilometers and a resolution of 5 by 20 meters. We have another important mode, which is the extra wide swath mode. Basically, that is, most of it is, we are using it for sea ice. It has a larger swath of 400 kilometers, a coarser resolution, but the wider swath allows us to have a much better revisit on ground. And this is what basically the CI services, national CI services, they were looking for. They prefer to trade off the resolution with the swath. And we have another mode very particular to the ESA missions, this one, because I think that we are the only one that have been proposed this mode. It has been recently also placed in some Chinese payloads, which is a wave mode that is used by default over ocean if there is no other modes that is required. Programmatics, we'll see that later in my next slide. In terms of operations, I think that it's important to mention that Sentinel-1, like all the Sentinels, have systematic data acquisition patterns using a predefined observation scenario. This is very often a request that we have from our user is to be as boring as possible in terms of observation scenario. Don't change. Stop changing observation scenarios like we were doing before with previous missions. And we have a very important instrument duty cycles of 25 minutes per orbit that we can increase to 30 minutes per orbit outside the eclipse. That represents 9 months over 12. And the rest of the orbit we can operate in low bitrate mode, being the wave mode. In terms of mission context, I think that this is a slide that you only see for Sentinel-1 because the Sentinel mission is really running in a complex context. After the loss of Sentinel-1B, premature loss of Sentinel-1B back in December 2021, the mission is fully relying on the Sentinel-1A unit, and that have now reached 10 years of operation, and that is really seeing or showing concerning signs of degradation for the first time ever in the missions. And I myself really believe that we are extremely close to have a description of the mission. That's why we are extremely we are looking for launching Sentinel-1C and D as soon as possible. This has been our objective together with the European Commission over the last 2 years. Sentinel-1C was supposed to be launched in April 2022. However, due to what we call now the European launcher crisis, it has been postponed several times. We are now looking ahead to have a launch of Sentinel-1C in the 27th of November this year. So we are touching wood, crossing the fingers for everything to happen, because with the status of the Sentinel-1A spacecraft, we are in a very difficult situation. Sentinel-1D will be launched as soon as possible after, because our objective is really to establish the constellations of 2 satellites as soon as possible. This being said, the picture is not that bad. Sentinel-1 has been since a decade the largest provider of SAR data in the world. I haven't mentioned that, but the largest provider of SAR data that is free and open. And I think that the fact that the data is free and open is something that has been key for the entire scientific community to leverage the use of SAR at scale. Sentinel-1 is unique. There is no alternative to it. If you look into other missions, you can look into the slide that have been shown before. If you look into other missions and try to find an alternative to Sentinel-1, either in terms of coverage, in terms of timeliness, repetitiveness, there isn't. So really Sentinel-1 is unique, and we are working very hard to avoid disruption of data as much as possible. However, the loss of Sentinel-1B has compromised our capacity to achieve global coverage. You can see here in the slide that represents the data collection that we have over the last year, that we have several holes here and there. This is because 25 minutes per orbit, it's a lot, but it's not sufficient. It's not sufficient to achieve global coverage. What is important to recall is that our current observation scenario is tuned to preserve the time series worldwide. We could have, after the loss of Sentinel-1B, we could have made choices. Do not acquire over Africa, do not acquire over Australia, South America, and put the focus over Europe, for example. But no, we decided to maintain as much as possible the time series worldwide, and to allow for the science to continue in these areas. What is important to mention as well is that we are now at our maximum capacity, and there is no possibility for us to increase the acquisition anymore. Okay. In terms of imaging modes, so I think that I'm exceeding my time already, so I'm gonna be fast on that. We have 4 modes, IW and extra wide. You can see here all the characteristics of the different modes. The main characteristics are the source and the resolutions, and you can see that basically there is no free lunch inside. If you want to increase the coverage, immediately you decrease the resolution by almost the same factor. So I don't go much more in details with these slides. I think that you can have the time to look into them after that. I think that what is unique with the SAR missions, it's of course its capacity to go through the clouds, and that makes these missions very key and probably your best friends if you are looking for work on snow, on ice, on glacier, because those are really areas where we have clouds. Sentinel-1, being an active instrument, doesn't have any problem of acquiring images night and day and whatever is the weather conditions. And you can see that with this global mosaic that we have generated for the month of December 2023. You can see really our capacity to achieve acquisitions everywhere over the land masses, but not only over the land masses, also over cryosphere instances. There is some echo on the line. Huh?
So, yeah, I don't know. There is some noise, but you need to close now because we are
okay.
far over the time. Yeah.
That would be my last slide. I think that it's very often difficult to measure the success of mission. One way we have is to measure the peer review publication that we have in missions, and you can see this slide shows basically all the number of publications that are relying on Sentinel-1. I think that what we have seen over the last decade is that Sentinel-1 is the backbone of most of the SAR-based services and applications. It's also the sensor of choice for an ever-increasing scientific community, and we can see that from the number of publications that have been increasing almost linearly over the last years. And if you compare that, if you make the same kind of queries with all other sensors, you can see that Sentinel-1 exceeds by far all the other sensors. And this is thanks to the people that is in this room. I think that contributes for their work in terms of making Sentinel-1 a success. So I will stop there. I was having many other slides in terms of applications. I'm sure that you will see them. You'll see other applications through this training course. I will stop there, and I leave the floor open for questions.
Thank you very much, Nuno. I don't think we have time for questions now, but we have a little time for questions. Normally I have 11:15 or 11:20. So if you can join again then, Nuno, so then people can give a question to you at that time. Yes. Okay, thank you. So then we will pass to Ferran Gascon, who is the mission manager, for Sentinel-2. Please, Ferran.
Hello, good morning everyone. So glad to be here. I hope you can hear me first of all.
We can hear you. It's a bit like it's a bit loud or it's a bit distorted, but I think it can work.
Okay, I think there is a feedback loop.
Okay.
There is a mic open somewhere in your room.
Now it's quite good.
Okay, because I have now it's fine. Yeah. So I'll put full screen mode. Yeah, so good morning everyone, glad to be here to provide you a quick overview of the Sentinel-2 mission of the Copernicus program of the European Union. So similar to what Nuno presented, this is an overview of all the missions that ESA is developing, has developed or is developing. And you have here in green indicated Sentinel-2A, which was the first unit of the Sentinel-2 mission, Sentinel-2B, Sentinel-2C, which has been just launched, Sentinel-2D, which will be the fourth unit of the Sentinel-2 mission, and then finally the next generation, which is being prepared. So Sentinel-2 is the high-resolution optical component of Copernicus. So it's imaging all land and coastal areas with a geometrical revisit of 5 days at the equator with 2 satellites. The 2 satellites are located at 180 degrees separation over the same orbit. The local time of the sending node is 10:30 in the morning. The instrument on board features 13 spectral bands covering the optical domain from the visible to the shortwave infrared. Then the bands have different spatial resolutions, 10, 20 or 60 meters. So the 10-meter bands are in the visible near infrared. Then there are a set of 20-meter bands, for instance, sampling the red edge domain. And finally, 60-meter bands, which are used more for correcting the atmospheric effects. The swath is also something unique for this mission. So it's a relatively quite large swath, 294 kilometers, considering the spatial resolution of 10 meters, is a push-broom scanner scanning the Earth as the satellite moves around the Earth. And the data, as for all Copernicus program, is free and open and serving a large range of applications. So here is a comparison of Sentinel-2 bands, which you have on the upper part of the plot. Comparison with Landsat, which is the historical mission which was started in the 1970s, and which provides a nice complement in terms of historical coverage for optical high-resolution imaging data. So Sentinel-2 is working very often together with Landsat mission, and here you have a comparison of the coverage. Sentinel-2 does not cover the thermal as Landsat does, and for the thermal, the Copernicus program is developing a specific mission for that, which is a mission which is called LSTM. Here a recall of the schedule where we stand in terms of satellite launches. So Sentinel-2A was launched in 2015, Sentinel-2B in 2017. We had a few last week, the launch of, on the 5th of September, we had the launch of Sentinel-2C, which up to now is proceeding nominally. And today should be released the first image to the public from Sentinel-2C. And then there is Sentinel-2D, which is foreseen for the last quarter of 2028, and the next generation in the future, which will double the performances of the mission in terms of spatial resolution and in terms of number of spectral bands, will be launched in 2033 first unit and 2035 second unit. So few highlights on the mission. So operations are nominal, so that's always good to have a nominal mission. We have 2 satellites perfectly healthy and operating. We are operating an extended observation scenario. So from what was initially defined for the mission, this has been extended. And on top of this observation scenario, we also perform from time to time ad hoc acquisition campaigns based on user request. And later I will present an example of that. All data is available on the Copernicus data space ecosystem. You can Google that, and it's the digital platform where all Copernicus space component data is made available. Then also to highlight that the Sentinel-2 Collection 1 has been completed and products have been made available to users. And Collection 1 is a full reprocessing of the archive since 2015, which brings all the data to the same quality level and format in the same format. So there has been evolution of the product quality and format a long time. So Collection 1 is a way of aligning all the quality and the product format for the whole archive and making available in one go to users. And then finally to say that we are still serving a large range of applications in land, marine, emergency, security, atmosphere and climate domains. So Sentinel-2 is the most popular European mission, the European mission which has most peer-reviewed scientific publications. Then in the following slides, I will provide a few examples of application of Sentinel-2 which are ice or snow related, which I understood is the scope of the meeting. So first one is in terms of snow cover. So here an example generated by the Copernicus land monitoring service, where the snow cover fraction was derived from Sentinel-2 data. So you can observe here, compared to other missions, the high resolution allows to have a very fine granularity in terms of snow cover mapping. Here another example, this is more a quantitative product, sorry. So the albedo measured by Sentinel-2 and then also compared to the one obtained from Landsat and the Apex airborne data. Here quickly another example. So I'm browsing a bit faster because we don't have much time to go in detail, but just to give you an overview of the applications. Glacier mapping, also here in this example. Next one is glacier velocity, which is complementing Sentinel-1 measurements by providing north-south and east-west deformation of the surface. Then there is another example here, ice sheet and ice cap monitoring. So we have supraglacial lakes mapped by Sentinel-2. Here another example, river and lake ice extend. So in light blue you have ice not covered by snow, and in dark blue we have water, non-frozen water, and in red lake areas not covered by water. And finally here also some other examples of where Sentinel-2 data is used for snow and ice related applications. Sorry, the slides are switching automatically, so I have to come back. Just one sec, I'll try to remove the automatic switch of the slides. So, sorry, now should be fine. So here another examples, set of examples, sea ice extend, which is, so ice monitoring is performed nominally with Sentinel-1 by the Copernicus Maritime Environment Monitoring Service. Because of the cloud.
Sorry, Ferran. Sorry, I missed what you said, but you're trying to show something now?
Yeah, sorry, I lost the sharing of the screen.
Now, yes.
Thanks, Espen, sorry. So, as I was saying, so sea ice is also monitored using Sentinel-2. In this case, mainly for validating the sea ice charts which are generated by Sentinel-1. So it's a way of, when there are no clouds, Sentinel-2 allows to perform a detailed validation of the maps generated by Sentinel-1. And then there are all other applications like snow line altitude, monitoring, avalanche hazard assessment, etc. Oops, sorry. So in terms of, sorry, I don't know what happened with the presentation. Yeah, so in terms of ad hoc acquisition campaigns, also I would like to present an example of an ad hoc campaign that we perform for monitoring the inner part of Antarctica, which was reachable by Sentinel-2. So the inner part is not reachable because of the swath, which is 294 kilometers, but for all the rest, we managed to map Antarctica in an ad hoc campaign that we target to perform every austral summer. Oh, sorry. I'm really sorry about this is switching slides too fast. So here an example of this ad hoc campaign where the Vostok Antarctica base was acquired for the first time by Sentinel-2. So on the right you have an image of the Vostok Antarctica base. Oops, and again, I don't know what happened. Sorry for that. I think I go out of presentation mode and I will show the slides.
And you're already at 11 minutes also, Ferran, so.
Yes. So here an example of glacier monitoring. Here another example of supraglacier lakes or in Greenland. Here another example of algal blooms in Antarctica. So these algal blooms were detected with Sentinel-2 visible near-infrared bands, and they are these algal blooms have a role in the carbon cycle in Antarctica. And with that I conclude. Just with this image also, that was an ad hoc acquisition campaign over Iceland, where the volcano near Grindavik in Iceland was captured during the eruption in these twilight illumination conditions. And with that, Espen, that concludes my presentation.
Thank you very much, Ferran. Will you be able to connect again at 20 past 11, or so we can because
20 past 11 is already past. You mean
12? Sorry, 20 past 12.
20 past 12. Okay, I'll try to join.
Okay, so if you have a question for them, please wait until 20 past 12, sorry. Okay, thank you very much, Ferran. So now we will switch to the mission manager for Sentinel-3, Jérôme Bouffard. Please, Jérôme.
Hello, good morning. Here I am. Hope you can hear me well.
We can hear you well.
Okay, perfect. So I'm going to share my screen. Okay. Okay, that's the last one. Okay, you can see my presentation?
Now it looks good.
Perfect. So I will try to be quick and just provide you a very high-level overview of the Sentinel-3 mission status and characteristic. So I'm happy to be with you virtually today to present this couple of slides. My name is Jérôme Bouffard. I am the mission manager of Sentinel-3 and Crystal. So just a couple of words about the Sentinel-3 mission. I used to call Sentinel-3 the Swiss knife of space because it's a very versatile mission addressing a wide spectrum of scientific and operational application. Sentinel-3 is a multi-instrument satellite. It combines an altimetry payload with the STRAL instrument as well as optical payload with the ocean and land color instrument, the OLT instrument, as well as the SLSTR instrument, the sea and land surface temperature radiometer. It is a multi-thematic Copernicus mission providing a continuity to dataset provided by the former ESA, ERS, and Envisat mission for what concerns especially the altimetry payload, as well as the CNES spot mission for what concerns the optical part. The main objective of Sentinel-3 are very wide. It addresses both the ocean, land, and atmospheric domain by measuring the ocean surface topography with altimetry, as well as ocean and land surface temperature and ocean and land color with high accuracy and reliability. Sentinel-3 also addresses other thematic domain and application based on vegetation, atmospheric, inland water, as well as sea and land ice, even if it is a secondary objective of the mission. And I will show some example today about the sea and land ice application. For what concerns the mission status overall, the mission status of Sentinel-3 is nominal. We have today a satellite constellation of two satellites, which are jointly operated by ESA and EUMETSAT. We have Sentinel-3A, which has been launched in February 2016, and the Sentinel-3B, launched in 2018. The missions are operating very well, with no significant issue to report. The overall status of the spacecraft and grace segment are nominal. We had a few months ago the so-called Sentinel-3 Missions Constellation Review Meeting, which held at EUMETSAT.
and confirming the good shape of the mission. The review was successful and confirming that Sentinel-3 is a standard worldwide mission with recognized added value, especially with regard to Copernicus services, which are our, let's say, main customer. Concerning the long-term continuity of the mission will be ensured with the future launch of Sentinel-3C. So the launch date is not confirmed and still subject to modification in the launcher manifest. But today the baseline is 2026 regarding the Sentinel-3C. For what concerns the Sentinel-3D, again, we are not sure today, but it will be later than 28. The satellites are today in storage, but even if the satellites are not yet in space, we are considering several options for what concerns the tandem phase of the Sentinel-3C. So how we will use together the 3 units in order to cross-calibrate the different satellite flying. So we have different scenarios discussed, especially with the support of the user community and iterations that we have with colleagues from EUMETSAT. And also we are discussing on what will happen after the in-orbit commissioning of Sentinel-3C with the possibility to keep one additional unit in topo mode only, but it's still to be confirmed. In terms of product responsibility, as I was mentioning before, the mission is jointly operated between ESA and EUMETSAT. EUMETSAT is responsible of operation, maintenance and evolution of the Sentinel-3 marine and near real-time atmospheric payload, while on ESA side, we are in charge of the land, the ice and non-time critical atmospheric payload and data processing. So I will here give you an overview of the product portfolio on ESA side. So for what concerns the altimetry payload, we have now a dedicated processing algorithm allowing to retrieve key geophysical variable over the inland water, sea ice and land ice domain. Just to give you a context, we have transferred to operation recently a new processing baseline allowing to improve significantly the quality of geophysical retrieval over these 3 different domains. Over the inland water now, the road tracking noise has been reduced by a factor of 4, allowing to characterize with a high quality the elevation over river and lake. So here you have an example of the retrieval of elevation over, if I remember well, it should be the Canal du Midi, so a very narrow river in the southwest of France. Over the sea ice, we have also significantly improved the retrieval of the sea ice freeboard, which is basically a proxy of the sea ice thickness. And now, thanks to the new processing method, we are able to retrieve this variable in a similar manner than what we are doing with Cryosat. So we can see here on this very small picture in the middle, the sea ice thickness derived, the sea ice freeboard derived from Sentinel-3, and for Cryosat showing a very, very good agreement up to 90%. So we are very happy because it means that now the 2 missions can be used in a synergetic manner. Similar results have been obtained also very recently over the land ice domain by using a new waveform processing method with an extended window of the delay Doppler processing, allowing to improve of about 25% the number of valid data, especially over the high topographic gradient region of the Greenland and Antarctic domain. And again here, the data product for Sentinel-3 are pretty close to the quality of the one obtained by the Cryosat mission. Concerning the optical payload, we are generating data both over land and for non-time critical atmospheric application with the SLSTR. We are deriving land surface temperature at near real time and non-time critical, so meaning 1 month after sensing with a 1 kilometer resolution. We are performing very regular quality control and validation based on in situ and global level 3 product showing a good quality of the Sentinel-3 data. We are also deriving a proxy of fire with the FRP product in MTC at 1 kilometer resolution. This product is also carefully validated with comparison with Moody's fire product. The Altier allow to characterize the global vegetation index as well as terrestrial chlorophyll index with a resolution of 3 meters and 1.2 kilometers, both in real time and offline. Also, this data product is validated by using independent dataset. We have also product of water vapor based on Altier instruments, showing also good qualitative and quantitative agreement when compared to ground-based observation. And also, what is also the particularity of Sentinel-3 is the combined use of the two optical sensors together with the so-called synergy product, allowing to derive, again, some vegetation-based characteristic and other parameters such as atmospheric optical depth, allowing to characterize aerosol and things like that. In terms of application, very quickly, as I was mentioning before, the spectrum of application of Sentinel-3 is very wide, but provide particularly good and relevant information for climate change monitoring, as well as extreme event, contributing to define index and essential climate variable for the long-term forecast of the environment. So on the right side, you can see some recent paper addressing multiple thematic domains. Just here, 4 examples, but again, I could give tens of examples by using both the altimetry and the optical payload. As I was mentioning before, Sentinel-3 is particularly useful to characterize and monitor the variation of water level over a river and lake, which is fundamental for forecasting extreme events such as flood. It is done thanks to the high long-track resolution of Sentinel-3 SRAL instrument, which allow to characterize many rivers. Today, we have more than 90,000 river and lake measured by Sentinel-3, including in the global land monitoring services of Copernicus. Thanks to the LST, the SLSTR instrument, we are also able to characterize the heat emanating from the Earth's surface, which is particularly important to characterize a heat wave, as it was the case 2 years ago across Europe. Here's an example, I think, of July 2023, with temperature higher than 45 degrees, measured in Bucharest and Rome. Of course, measuring the land surface temperature is also key for agricultural purpose and also to evaluate water requirement. Also, an application of interest of Sentinel-3 is the characterization and observation of a large wildfire from space by using different sensors on board Sentinel-3. We have today many products generated by ESA, including product for the Climate Change Initiative Fire and the World Fire Atlas. Also, I was mentioning before that Sentinel-3 is also used more and more in synergy with Cryosat in order to characterize and monitor the sea ice thickness over the Arctic and Antarctic domain. Monitoring the sea ice thickness is fundamental to establish relevant strategy to protect the polar environment. And when Sentinel-3 data are processed à la Cryosat, it provides an essential continuity of sea ice thickness observation up to 81.5 degree north. Given the fact that Sentinel-3 is in Caillou Bend, when you combine also Sentinel-3 sea ice thickness retrieval with the one obtained from the ALTIK satellite in K-band and ISAT-2, which is a laser altimeter, it allows also to retrieve a proxy of the snow depth. It is still a subject of research. So today we are not generating operationally a snow depth product based on Sentinel-3, but it's part of an element in order to be able to do so, which will be also particularly interesting in preparation of the Crystal mission, which will have on board a B-band altimeter allowing to directly retrieve this key variable. Here is an highlight of a recent application of Sentinel-3 optical instrument, the Altier instrument, which has been used to track snow, grade, and melting land ice over the Greenland domain by using a new algorithm developed in the frame of the ESA sea ice project. It has been possible to characterize snow grain size and albedo variation over the land ice. This product has been validated and incorporated in the DMI operational near real-time processing chain and are assimilated into a climate reanalysis. Here we can see a signature of an abnormal temperature in July 23 caused by causing an albedo anomaly that you can see on the time series here below. With that, I think I have finished. So I just try to be brief, and thank you for your attention.
Thank you very much, Jérôme. Okay, I think we have to do the same for you. That we, any questions for Jérôme, if he can connect? Sorry, sorry, I lost my voice. If you can connect again at 11:20, then we can have questions for you at that time. Now we
Okay,
need
I will try. I have another meeting meanwhile.
12:20.
Come back once my meeting is finished.
Yeah, so try to note down your questions for all the presenters so that we can ask them afterwards. So thanks again, and then I'll welcome Lorenzo Giannini, who will talk to us about the new mission ROSE-L. Please, Lorenzo. Your voice was not very loud.
Hello, do you hear me now? Do you hear me now, Espen?
It's quite, the volume is very low with respect to the others.
It's very low at the beginning, but I should improve because of my microphone calibration. Do you hear me better now?
Okay, it's getting better, I think. Yes.
Yes, I don't know, but okay, this is how it works in the latest days. Do you see my screen now?
Yes.
Pardon?
Perfect.
Yeah. Yes, so good morning, everyone. Yes, I'm here to indeed introduce ROSE-L. Sentinel mission scientist supported the mission. Marco Davison is the responsible mission scientist. ROSE-L stands for Radar Observing System for Europe in L-band. So it's a L-band mission that the L-band mission that is supposed to provide new information not yet available, so to fill some of the gaps of the other Sentinel missions. As you see here, it is expected to join Sentinel-1 starting from 2028. And you see here also Sentinel-1 next generation, in fact, that will join later, 2032, and it will push further this concept of enhanced continuity together with ROSE-L in this SAR ecosystem. So the message here is that the mission shouldn't be addressed in a self-standing way, but should be considered in a system of systems perspective and best exploitation. So some missions typically serve a lot of application domains, and ROSE-L is no exception. So we expect very essential information for geohazard monitoring, land use, agriculture, forestry, food moisture, marine and maritime monitoring, and the last cryosphere and Arctic on purpose. So now I will cover a few highlights for a land cryosphere, starting from land ice monitoring. So ROSE-L will be a game changer for glacial movement and ice sheet velocities. So as you know, probably L-band is a longer wavelength, with a longer wavelength than C-band, so a longer wavelength that is more sensitive to larger and stable features than C-band, which means it's also more obvious to temporal decorrelation, for instance, due to snow drift and accumulation. And in addition, it has improved the phase enwrapping for challenging areas such as shear zones and fast-moving areas. And this enhances significantly the use of interferometry for these kind of applications, filling the gaps C-band. And another application that, for instance, benefit from this kind of robustness is the monitoring of the identification of the grounding zone. This doesn't mean that Sentinel-1 will not be useful anymore, of course. In fact, we have to aim at a combination of the two missions in a system, again, in a system perspective, to address past processes that this will allow to have us a very short revisit to find will be very relevant. Another highlight is seasonal is the contribution, the novel contribution for seasonal snow monitoring. So we know that Sentinel-1 is already very useful in providing wet snow maps, so wet and dry snow discrimination is what C-band is very suitable for. In addition, L-band will is supposed to bring information, novel information on the snow water equivalent, and thanks to this capability of L-band of being more stable in snow conditions. So this should follow also a little bit the consolidation of the interferometric model. So this working as an interferometric application. You see here on the right, there's an image of two images of two coherences from that were collected from an urban campaign over a snow-covered mountain area, and you see a pair, the coherence for a pair of C-band images and the one for a pair of L-band images, and you can see that clearly that the L-band is brighter, which means that it's more coherent, which means that it's a little bit easier to retrieve information from each space. Last highlight is about permafrost monitoring. So L-band will be crucial for subsidence monitoring within the permafrost transition zones and coastal areas. This is for this capability of penetrating better than C-band in vegetated and snow-covered areas, and to its robustness to phase unwrapping. So this will be very useful, especially in a location where there is fast movement, mass movement. Of course, together the two will provide augmented monitoring of land surface, so for example for freeze status, again, water equivalent and other information. In order to make this big overall contribution for land ice, cryosphere in general, but also other applications, this is how the mission has been designed. So it's a big machine. I will not focus on the instrument, which is also very interesting, in fact, but I will just limit myself to say that it's a very big phased array antenna. You see almost 40 meters square, which is 4 times bigger than Sentinel-1. But the main aspect, I would like to focus on the key aspect here for mission, for applications. So the constellation is composed of two satellites called Protoflight Model and Flight Model 2 currently. It's a very ambitious coverage requirement because it will cover globally and the Arctic, and but we will have a repeated frequency with two satellites combined of 6 days over the global land, 3 days over Europe, and daily in the Arctic. And very important for the application I just showed, there will be a repeat cycle of 6 days, in fact, like Sentinel-1, but everywhere on the global land with two satellites. It is also programmatic. It is currently in PC, so there will be the end of the PC at the end of the year, or in fact the beginning of next year. And the qualification acceptance review of the first model, the Protoflight model, is expected in 2028, so the launch will follow soon after, hopefully, and the second model delivery is expected in 2029-30. In terms of imaging capability, indeed is a big machine, the highly performant one as well. It will have a dual pole mode. It will support the dual pole mode as the main mode. The workhorse mode is mode called RIWS, so Roselle Interferometric Voice Mode is the current name. But it also supports the quad pole mode, QWS, is quad pole voice mode. And there's not interferometric, but it is interferometric. And we will also have the capability of supporting wave mode, and it's not present here, but also there's the option as we studied for extra wave mode, kind of similar to the Sentinel-1 extra wave mode. The resolution for the main mode is 50 meters square, so 2 times better than Sentinel-1, and there's very low noise floor and low ambiguity level. About the synergic aspects, I will cover it in the next slide, in fact, because it's an important design aspect. So the main thing here is to understand how it will combine with Sentinel-1, because an optimal exploitation of the 2 missions, in fact, we chose to have the same orbit, Sentinel-1, and so we face the satellites, we face the orbital plane. So that we adjust the orbital plane in a way to follow the same ground track of Sentinel-1, and also the mode will be guaranteed to have the SWOT of the dual pole mode, the RWS, is guaranteed to have full overlap with the Sentinel-1 RWS. This means that there will be the same geometry observing scene, and it will be very important for the application. Another mission design aspect is the phases, so they support 2 options. The moment is not decided which one of the 2 options will be pursued at the end, but there will be both options for optimized phasing for reaching capacity visit, so interleaved every 3 days, so Sentinel-1, Roselle, Sentinel-1, Roselle every 3 days. But also there's support for option of a convoy with Sentinel-1, up to 1 minute distance, so not closer than 1 minute. This is also supported. In terms of coverage, I would like to stress again the fact that it has an extensive coverage. If you see this sizing scenario.
Excuse me, Lorenzo,
yes.
you can finish now, or?
Yes,
you're over the time already. Yes, thank you.
Yes, so a lot of this a big duty cycle, and the Sentinel-1 we have free, full, and open data policy. And I think it's finished, and so I reached my conclusion, just stressing that again, this should be addressed in the system of systems together with Sentinel-1 and other photo missions. Yeah, I will leave the floor to you.
Okay, thank you very much, Lorenzo.
Thank you.
And hope you are able to connect again 20 past 12 or 25 past, I guess. I think we can start the discussion. Yeah. So with that, I will invite Ben Cutts, who is the mission scientist for our future land surface temperature mission. Are you there, Ben? Hello, Ben.
I don't see Ben connected. No. It's Marco speaking. If
it's
you
not
want, I can start.
That would be great. So then we start with the CHIME's, future CHIME's mission will be presented by mission scientist Marco Celesti. Please, Marco.
Good morning, everyone. Thank you for the invitation. It's a pleasure to share some thoughts on CHIME, particularly related to monitoring the cryosphere. Just a moment to share my presentation with you. You see my presentation in full screen mode?
Yes, we see it. It's fine.
Well, wonderful. As has been mentioned, I'm mission scientist for CHIME, the Copernicus hyperspectral imaging mission for the environment. The CHIME is part of the 6 Copernicus expansion missions that have been introduced already with Roselle and others, and will provide routine hyperspectral measurements in support of European and related policies, in particular focusing on food security, agriculture, and raw materials, but without forgetting that there are a number of secondary applications which will benefit from CHIME observations, and some of these are clearly related to cryosphere applications and science development. We will show some of these. We'll see some of these in a moment, but. Couple of words on CHIME itself. It will provide carpet mapping observations, so routine monitoring observations a la Sentinel-2 of land and coastal areas. The current mask is up to 370 kilometers offshore, with a maximum solar zenith angle of 84 degrees. With a ground resolution, a pixel size of 30 meters over a swath of 130 kilometers, which provides, with 2 satellites in orbit, a revisit of 11 days at the equator and a slightly better coverage time at northern latitude and southern latitude, of course. For each of these pixels, the spectral range which is covered is between 400 and 2500 nanometers, with a continuous sampling of about 8.4 nanometers and a full width of maximum, so a bandwidth for each of these channels of about 10 nanometers. The design of the instrument allows for high radiometric accuracy, very high SNR, and very low spectral and spatial misregistrations. We will have a number of user data products, both top of atmosphere radiances and reflectances, and bottom of atmosphere, sorry, I don't know why it's automatically going on, and bottom of atmosphere products of surface reflectance in sensor and auto-rectified geometry. All these with associated uncertainties to guarantee that downstream products can be then provided with, let's say, an appropriate degree of confidence. But how will CHIME be relevant for studying and monitoring the cryosphere? I'm showing now a couple of examples provided in kind by Roberto Colombo and Biagio Di Mauro, based on existing observational capabilities, particularly from Prisma, NMAP, and some field campaigns. And CHIME will be able to provide the same or better level of quality of these products, but bringing a monitoring capability into place. So just seeing these examples as a snapshot of the future, basically. With the spectral range and the spectral characteristics of CHIME observations, we are able to retrieve a number of snow and ice properties. Here, in particular, an example showing retrieval of grain size and impurities over the Aletsch Glacier, starting from Prisma data, which is, as I said, a sort of precursor for CHIME from the Italian Space Agency. Also, we have sensitivity to liquid water content in snow from hyperspectral data, some absorption features which can be exploited for that. But we know that observations over the cryosphere are also extremely useful for validation purposes and for intercomparison purposes, because as you can see here on screen, basically in certain conditions the surfaces are basically the closest that we can have to a spectral on panel, which is what is a perfect considered the closest to a perfect diffuser that we have. So, but with a spatial size that we can really use from space. Another example here in Greenland of the capability that we have to retrieve ice parameters from hyperspectral imaging, and you have the references to look further into that if you're interested. With an example of retrieving the mass, the algae mass mixing ratio, and the spatial component which is provided by this imaging missions allows for also spatial analysis and transects, which would really not be possible in the field. Here, I just, again, for your information, I will add to leave in the presentation some QR codes to know more about CHIME and some more material that we have. And with this, I thank you very much for your attention.
Thank you very much, Marco.
Okay, yes.
Thank you very much. Do we have Ben connected now? If not, if you have, we could take one question to Marco now. If somebody has a question immediately. No, okay, then if you have the possibility also to join again or stay on, Marco, then we can see if there are questions afterwards.
I will try my best. If not, I can take questions offline anytime. Thank you. Enjoy the week.
Thanks for that. So I don't see Ben, so I think we will go on with the presentation on crystal by Paolo Cipollini. So please, Paolo.
Yes, good morning, Espen. Good morning, everyone. Thanks very much for having me. Let me just share my screen and my presentation. It's a pleasure to be able to add this little bit about crystal to the presentations that you had in the last few talks, because I think it complements quite nicely what has been said about the other Copernicus missions. So there it is, and we should be able to see it. Please confirm that you see now the presentation.
Yes, now it's perfect.
So yeah, I'll briefly introduce the crystal and also allude to how we're going to use it for monitoring snow and glaciers. So you've seen already in the presentations that were before me this morning, many of those missions that you've got in this slide, which depicts the Copernicus context, so the full constellation of missions that we've got for Copernicus. And you see we are now dealing in the last three talks with the Copernicus expansion missions, of which crystal is one. It would be it would be a system of two satellites, not exactly a constellation, because we'll launch them in sequence. So we'll have crystal A first, and then crystal B from when crystal A ages, and I think crystal A we will launch in 2027. So it's coming pretty soon, and this is another illustration of this expansion in the Copernicus family, with the family of the 6 new sentinels. You see crystal in the lower right corner, and you heard previously about CHIME and Roselle. They are all quite useful to monitor snow and glaciers. Let's see how, in particular for crystal, we are dealing about an altimeter. So we essentially measure elevation. And in this slide, there's the main features of this mission. And I've highlighted in red those that are most importantly to look at snow and glaciers. So, for instance, there will be a dual band altimeter, Ka and Ku, and the idea of adding these dual band capabilities is that by comparing the ranges in the two bands, we should be able to measure the snow layer, the depth of the snow. And then there will be, amongst the technicalities of the mission, there will be a flexible tracking of the altimeter, which means where you position the window, the listening window of the radar to get your echoes back. And when you got this flexibility, you can follow rugged topography, which will happen, for instance, over alpine glaciers without losing lock on the surfaces, which means that the altimeter keeps following the profile of the surface and the topography. And then in the acquisition mask, we will have a full coverage, not just of the cryosphere, the oceans, the coastal areas, but also the inland waters, which are an important target, and all the glaciers. So we will have crystal data over all the glaciers in the globe. And I want to show this one, which comes from an airborne campaign where they had a Ku and Ka band altimeter on board, which shows in the radar grams, the pictures on the left, the difference that you get from the two different measurements. So with the Ka band that really sees the top of the snowpack, and the Ku band that penetrates inside, and you get multiple reflections from all the different layers. Again, these are airborne data with lots of power and higher range resolution, but from space we have research and development to do to exploit the data that we expect from crystal to resolve this layering in the snow, and possibly being able to measure snow depth even over land. We are, like I say, doing funding research and development to look at how to use this dual band approach. There was a workshop which we hosted already 3 years ago. You can Google dual cryo and find the report of this workshop, or come back to me and I'll provide you with a copy. But the important thing is that we are also building our own airborne demonstrator. It is called Crystal Air, which will have an airborne altimeter with dual band capability to measure snow on top of the ice, and that we are planning to use in a number of different campaigns. So this will be an additional instrument available to the scientific community, with which we could go and explore glaciers, for instance, alpine glaciers as well. In fact, we are planning to test it very soon, because it should be available, like I say here, in early 2025. We're planning to test it over alpine lakes to resolve the thickness of the lake ice and also the depth of the snow on top. Crystal has as application sea ice, which I don't cover here, but also land ice and inland waters. And among land ice, of course, we're looking at the big ice sheets over Greenland and Antarctica, and the differences, the changes in those surfaces. But it's been demonstrated already that you can monitor polar glaciers. This has been done with Cryosat, the altimeter mission, which is a precursor of crystal, and which has been operated for already 14 years as an ESA explorer. Cryosat, a very successful mission, and some of the Cryosat data have been used to derive those maps that you see in the top right picture in this paper by Jacob and Gurmelen, looking at the changes in polar glaciers around the world. And we can exploit the fact that Cryosat and Crystal have two antennas, so we can get an interferometric measurement and explore also across the track of the swath, doing the swath processing. The applications of crystal to hydrology of water, of course, include glaciers, mass balance, and meltwater dynamics. This is easy to do over larger glaciers, over the big expanse of ice in Antarctica and Greenland, and over the large glaciers on the margins of those polar continents. It will be more a matter of research and development to push the resolution of our observations to the limits that is required by smaller glaciers, but we are certainly going to do it. So, for instance, of something like the Uppsala Glacier in Argentina that you see here in 1928 and 2004, we are already confident that we'll be able to follow the evolution of the melting of the glacier quite nicely. And these kind of applications have already been used for global reviews of global ice mass change in glaciers, like this paper by Zemp et al. In 2018, published in Nature, and based on the ISA glaciers CCI research. But we hope that we'll be able to go even to smaller glaciers, like I've got here a map of the Swiss glaciers and the dramatic change that it was observed in the past season in 2023 with variations exceeding 2 or 3 standard deviations with respect to the climatology. My point is that monitoring the evolution of glaciers is a challenging but very important objective for crystal, and there is mounting evidence from altimetry that this can be done. I'll make just an example, and I'll conclude with this example on a smaller glacier, the Pers Glacier in the Bernina Group in the Alps, which you see here. This is what you see from space, Pers Glacier, which is about 3 or 4 kilometers across. And the orbit configuration that we have for crystal has a long repeat cycle, about 1 year repeat cycle, which means that every year it will go over the same track again, but the mesh of tracks is quite dense. So when we look at the orbital ground tracks that we've got for crystal, for instance, you can see that there is a track that goes over the Pers Glacier every year, and hopefully it should be possible to monitor the variations in elevation over the track year after year throughout the duration of the mission, which is a mission of 2 satellites in sequence, so for approximately 20 years. And there it is, where the track goes over the glacier. So my summary slide, a take-home message. Altimetry has already an operational status for monitoring large expanses of ice, so the ice caps, the ice sheets, sea ice, large glaciers, and crystal is the operational mission for the cryosphere for Copernicus. When we go over smaller glaciers, we are still at the level where we are doing more research and development, but there are features in the technical capabilities of the instrument that allow us to look at glaciers. So for instance, with SAR mode altimetry, we get higher long track resolution. Along the track of the satellite, we can resolve every 300 meters or less. The flexible tracking on the instrument allows following the surface when it changes rapidly, so over steep topography, and that's what I call open loop tracking. Interferometry, so having 2 antennas and exploiting the phase difference in the signals that are received by the 2 antennas, allow us to explore the topography across track, and this is possible, of course, even across the glacier. And then the dual band approach allows the estimation of the snow depth, because the Ka band is reflected mostly by the top of the snow layer, and the KU band penetrates inside, and in fact it can resolve some layering in the snow until it gets to the base of the snowpack, the surface of the ice. And this is possible potentially also over land ice and over land. So altimetry will give us this information about elevation and depth. And my idea is that this is especially valuable when it is integrated in a multi-mission, multi-instrument observing system for glaciers and snow. So when it's integrated with other instruments like what we've seen from Roselle, what we've seen from CHIME in the previous presentation. And please note that we have a SAR mode altimetry that we're working on already available from Cryosat 2, Sentinel-3, Sentinel-6 that has been already used to look at glaciers. And Crystal will continue this and will bring altimetry for the cryosphere to operational status, having a dual band capability. And we plan to launch Crystal A in the second half of 2027. We are already in phase D. We've passed our critical mission review, critical design review of the mission in June this year. So we are now proceeding with actually building, assembling the satellite, and hopefully ready for launch in 2027. In the meantime, in just a few months, we'll have the airborne demonstrator, Crystal Air, which should be also useful to look at alpine glacier, and we indeed are planning to use it for that as well. Thank you.
Thank you very much, Paolo. So then we will have our last presentation, and then after that, in 10 minutes time, so then we're normally at the lunch break, but I will ask if we can continue a few more minutes afterwards, if you have some questions. And it would be nice, it's a very nice opportunity to have some questions to ask to these persons who are responsible for these missions. So with that, I will invite Ben Katz to do a presentation on our future land surface temperature mission. Please, Ben.
Thank you, Ben. And I hear echo.
I will switch off mic, maybe it's better then.
Okay, great. No, thanks for the introduction, and happy to present also the land surface temperature monitoring mission, which is about land surface temperature, very much related to agriculture monitoring. But I mean, I understand you're very interested in the, let's say, more icy part of the earth. Still, temperature matters to keep or to manage these type of environments. So I hope we can make a case also that this information will be quite breaking in terms of new information. So I'm sharing my screen.
We can see it perfectly.
Okay, thank you. I always like to start saying that this mission is really supported by a lot of different type of people. I mean, first of all, you see here the people from the mission advisory group, which me as a mission scientist are kind of facilitating, but there's also a huge number of people inside ESA who are like running the projects to make all the engineering work to make actually the mission a reality. And that is actually quite an amazing task over years to develop such a mission. So next slide, you have seen that slide before, just to place LSTM somewhere between the food security and water management part, where LSTM can make a big impact, as well as combating climate change. And I think that is where we can also make the links to glaciers and ice sheets in a way. So the real reason is here making the impact for LSTM very clear. And if you see here the IPCC report, text report, highlighting a number of risk in Europe, but I think we can even in an exaggerated way make the same case to other places in the world. Is we want to manage the human heat stress, so that's really about health issues. We're talking here even about mortalities. You can make a link to increased death during certain heat waves. It's scientifically proven, and you need to make sure that there's climate adaptation plans and on the national level trying to forecast, manage this in a way, especially in the urban environment. But then the other part is the water scarcity in Southern Europe, but actually also in other parts of Europe, where we have droughts and we would need to manage the water being used by agriculture. So saying irrigation is one of the key applications which you can manage with and the LSTM measurements. And that would avoid losses in crop production, which is the third key risk, which we can address with LSTM at scale where we can actually manage and make evidence-based type of decisions. Just to give you an idea how that looks like, on the left-hand side you see the water productivity, so we can actually with models together and simulate and measure the loss of water from a crop, from a field, its intra-field variability in terms of evapotranspiration. So we can quantify that, and then after the day of evaporated water, the farmer can replenish that at the next morning if he has the right information. Otherwise, he will just overwater or do whatever he can, but not optimize, and water being scarce is a limitation. So we would really make up to 30%, some of the science studies says, can be saved in terms of water being used and extracted from the ground, for example, in certain areas, which make a real difference. On the other side, urban planning, the urban heat island, I already mentioned it. You see here Milano, you see Athens last year, but also this year we have examples which are quite dramatic. And Spain, all of them, including my hometown here in Rome, are suffering and getting temperature in the city which are not really bearable anymore. So we trying to use this kind of spatial disaggregation to help urban planners to make countermeasures in the urban space. So that all leads us to the emission objectives. We want to have high spatial temporal resolution in the thermal infrared in support of agriculture management services. As I just pointed out, that is our driving mission objective. It really is the point where we design, optimize the mission for, but then there's a range of additional applications, and that in your point of application range would be permafrost, would be glaciers, would be perhaps even the Antarctica, how the melting is progressing there and how that is changing the environment, and also the water cycle. And that, I think, is a very important application. And we will try to make sure that the mission is addressing and supporting that. I will come back to that in some of our slides. So based on the user requirements, basically, that you need to have at field scale daily observations in a certain accuracy so you can understand the evapotranspiration. We have designed the mission, and you see here on the left-hand side the different key features from the revisit, the resolution. We have 50 meters as the across the swath needed requirement, but we actually go down to 37 meters at nadir, which we can exploit. Then the right spectral bands, and to make a higher revisit actually possible with 2 satellites, we have a quite extended swath, which comes with its own limitations. I will come back to most of these requirements in my following slides, so I will not go into more details, but I mean, this is the core requirements we have to meet. Then what we will deliver as a mission, we really focus on the main products. So at level 1C, there is the radiometric and geometrical top of atmosphere radiance for the optical visible part. And then for the temperature and thermal parts, so 8 to 12 micron, we will deliver the top of atmosphere brightness temperature. And for the real information products, there you will have lens surface temperature, emissivity, and some of the intermediate atmospheric correction parts, which are in itself also of interest. Where I have to highlight here is, as I mentioned in the beginning, the farmer needs at the next morning actually the type of information, how much water he has to replenish. This kind of water requirement is quite dynamic. We need to be very high, delivering in very high data latency. So you see that the lens surface temperature, we are trying to meet at least a 12-hour latency, and that we will deliver at least over Europe and Africa in this sense. You see here the constellation, and 2 satellites are flying in constellation. So we can actually meet these 2-day revisit, and the revisit is defined really at the equator. It's a constant angle. Obviously, you will have additional overlapping orbits in the higher latitudes, like in Europe. So there we will have higher revisits, and for sure in Greenland and other places there will be a multitude of overflights actually. And you see there's a huge swath, and that also comes with a certain directionality across the swath. So we will have view angles up to about 27, 28 degrees, and then we need to take this into account and also be working on the science level to correct for these things. And this has never been done really, because this type of information in the thermal range is not so much used at 50 meters resolution up to now. So in terms of coverage, we really much focus on the land type of mission, but there's also coastal areas, and as you see also some of the islands and the Mediterranean. Greenland is fully covered. And what we have not really put into the mission is the Antarctica, but we do have made some feasibility studies, and we will consider at least campaigns. So, like for example, the summer, the southern hemisphere summer, having dedicated observation windows. But we could even, and that is something which the mission is considering, to include a certain melting zone, and we have worked with different scientists who works in Antarctica to define this better, so we can actually include permanently also the melting zone of the Antarctic. So to give you an idea how the observation acquisition concept would work, it's not a push broom like Sentinel-2, it's actually a whisk broom, so we can actually, that's driven by the large swath. We need to switch over to that type of acquisition concept. It is helpful to get all the right information in a very controlled environment, but at the same time, it has impacts on the signal to noise ratio because the observation time is relatively short. Then, in terms of spectral bands, you see we have in this near infrared part more or less the same bands as Sentinel-2. So there's consistency as well, and it helps us to understand the vegetation and other aspects. But then we have 5 thermal bands from 8.6 micron up to 12 microns, and that helps us to directly receive also the emissivity together with an independent LSTM, so lens surface temperature measurement. In the meantime, we're waiting for the launch of the, building the satellite and launching it eventually. We are having several airborne campaigns. You see here 21, 23 airborne campaigns, which we have been conducting, and these data will be very soon available for the full community. Especially also interesting is that we have the last time overflights from 2 airplanes looking at the same pixel from different view angles, and that could be helping us to correct for this directionality which I was mentioning earlier, and I think that's a quite interesting concept. I'm sure over snow and ice that is also an issue, so something to look into your science backgrounds. So finally, I would like to conclude that we do actually are not alone. We work together with 3 missions. LSTM has 2 platforms, so LSTM A and B, but then there's also Trishna, which is a cooperation between CNES and ISRO, India, as well as the SDG mission, which is run by NASA and ASI. We have managed to get them all aligned with the same orbit and the same solar local time. So it's actually really comparable data sets. And with that, we could come up to even a daily overflight. And that's quite powerful in terms of temporal resolution. And that we hope for to get this going. And Trishna is supposed to be launching also quite earlier than LSTM. But that's, yeah. And hopefully in 26, there will be already the first thermal data in this very similar resolution. With the final slide, I'll just give you the update on the status. We are in the in the middle of the critical design review. So the instrument is being reviewed, and at the end of the year, we also have the system. And with that, we would be fully on track to have a protoflight model ready to be launched in the end of 28. So most likely being launched in very early 29. With that, I conclude, and I thank you for your attention.
Thank you very much, Ben. Okay, so do we have any questions to Ben on the LSTM mission, or to Paulo on the Crystal mission, or Jérôme on the Sentinel-3 mission? I think we have lost some of the others. No.
And Espen, I'm also here connected with Jérôme, and Ferran speaking.
Okay, perfect. So on Sentinel-2 mission also, if you have a question for Ferran. Nobody has any question? Yes, please.
So what can we expect in the future?
Just wait for the microphone. Yeah. Doesn't work. Or maybe you can come down here. We have a little microphone problem. Sorry about that.
So what can we expect in the future from Sentinel-2 when it comes to the spatial resolution?
Yes, so I think it's a question for me. The spatial resolution for the next generation will double, so it will go from the current 10 meters to 5 meters, and from the bands which are at 20 meters, they will go to 10 meters. So it's a factor of 2 in terms of improvement in spatial resolution.
Thank you. Any other question? So just to tell you that people have not had lunch yet, so of course they are also hungry.
Same for us.
No other questions?
Espen, can I just cast a comment following on the previous question about the improvement in resolution expected for the Sentinel-2 next generation mission? I really would like to add that we will also be improving the performance of the Sentinel-3 optical mission, and we are planning to achieve resolutions of the order of 150 meters, which might become relevant for the larger glaciers, given that we will also have a frequent revisit of the order of 1 day. So there's probably going to be an interesting synergy from the great detail that you get from things like CHIME, LSTM, and Sentinel-2 next generation, and the medium resolution but very high revisit that we will get from Sentinel-3 next generation. And these should benefit snow and ice applications indeed.
Thank you, Paolo. So, yeah, now actually we have some, please come down here.
Thanks so much for your presentations. I wanted to ask something similar about Sentinel-1. How are the specifics about the next generation Sentinel-1? And also if there is dual pole or quad pole there? If anyone knows.
I can. I also support Sentinel-1 generation. Nuno is not here, so I can reply maybe. So the resolution of the next generation will be 5 by 5, and the support is for quad pole is there. So the capability for both quad pole and quad pole is there. Whether they will be equally distributed or all quad pole or mainly dual pole and just quad pole for some areas is still to be decided, of course. Quite early in the schedule.
Thank you, Lorenzo. I think we had at least one more question. No? Yes? And those who have other questions, please come down at the same time so we can quickly move to the microphone.
Yeah, hello. I have a question to Paolo, that how we are taking care of the fluctuations in the radar signal in crystal.
Sorry, can you repeat the question or not? How we are taking care?
Yeah, of the radar fluctuations in the crystal. Radar fluctuations.
Fluctuations of what, sorry? No. Apologies. Fluctuations of?
Radar signals.
Okay, yes. Yeah. We will, thanks, it's an interesting topic. Indeed, with our altimeters, we obviously do not only measure the timing of the reflecting impulse, but we also measure the strength or the power of the reflecting pulse, and we can convert it into what we call the radar cross-section of the target. And it is a matter again of research and development to be able to use the information available in the radar cross-section, especially when we will be measuring that cross-section in two different bands, and to use it to derive information on the targets. In principle, it is strongly related to the roughness of the surface, but it also depends on the scales of the roughness. And like I said, there is valuable information in there, but we certainly need to carry out more research and development to exploit it. There could be also information which is relevant to permafrost science, because it might be related to the state of the ground in Arctic regions, and it could be derived. It could be used in combination with what we get from infrared observations to assess the status of the ground. So for permafrost studies.
Thank you very much, Paolo. So you have a last question, and we have time for a short answer.
Yeah, I also have a question regarding the Crystal mission. So as far as I know, there is like also the terrestrial SNOMES mission from the Canadian Space Agency, who are also using like dual frequency with Q and K-band radar. And I wanted to ask, what is the difference, and are there like any collaborations planned between like different missions in that context?
So they work on similar concepts, and we are now at this stage of starting the discussions with the Canadians to maybe carry out some joint campaigns. Airborne instruments will help a lot to refine the algorithms, and we should make sure, although again the discussions haven't started as yet on that there is a proper intercalibration in the future. I can tell you that Canadian scientists are involved in Crystal and provide advice to our mission, so we will make sure that this is continued and put into effect when then the mission is operational, and we'll have a joint calibration.
Thank you, Paolo. So thank you for the questions, and thanks a lot to all you mission managers and mission scientists, even if there are not so many of you left now, but thanks a lot to everybody. And just if I can ask you while I have you here, that if you can send me your presentation so that we can upload it, so people can look at it again and also share them with other people. Thanks a lot. Bye-bye.
Thank you, guys.
Thank you. Have a nice lunch, everyone.